Okay, so moving on to the next question. So suppose your singing voice has an intensity that's 3 times the student that's sitting to your left. So how much higher is your sound intensity level in decibels? Okay, so here we have to think about your intensity is 3 times as much, but how does that actually convert to dB? Go ahead and pause here. All right, so if you think that you've gotten the answer, hopefully you found that it was 4.8 dB higher. So how do these things actually, how do we compute these actually? So we can find here, switching to the camera, well, that's not going to work. Let's see, I need to press pause. Okay, so we looked at our sound intensity level in dB, and that's usually just 10 times the log of the ratio of intensities. But you could also say that it'd be the ratio of, for example, your intensity to their intensity, and that would be a sound intensity level difference. So we can do something like this. I can say sound intensity level difference here, and it's going to be 10 times the logarithm of the ratio of intensities. So here, really what I'm doing to compute this is I'm saying this is equal to 10 times the log of my intensity, which is 3 times the intensity of the other person. So in other words, my intensity we could say is I2, which is going to be 3 times I1. So in other words, we'll do 3I1 over I1, and then finally we'll get that this is 10 times the logarithm of 3. Okay? If you plug that into a calculator, you'll get approximately 4.8. We're going to go to sort of a more intuitive picture of this in just a moment, but I wanted to make sure that you know how to calculate these things. So in other words, intensities add with each other. If I have 2 trombones instead of 1, it'll be twice the intensity. If I have 3 trombones instead of 1, it'll be 3 times the intensity. But the catch is that sound intensity level dBs don't add. So as an example, if I had how many dBs does the sound intensity level increase when 2 trumpets play together? Well, so if you followed the example from before, we can actually just take 10 times the logarithm of 2, because we'll have twice as much intensity. Just writing it out here on my paper here, we can see that the sound intensity level difference is going to be equal to 10 times the logarithm of twice the intensity over the original intensity. So this will be 10 times the logarithm of 2, and if you plug that in, you're going to get approximately 3. The logarithm of 2 is approximately 0.3, multiplied by 10, you'll get about 3. I'm going to just say right approximately there. Okay. So there's a chart. This maybe help you to feel like you can do this a little more intuitively here. 3 dB is a factor of 2 in increased intensity. You go up another 3 dB to 6 dB, you go up a factor of 4. So every time you go up by 3 dB, you're actually multiplying by 2 in the intensity. Probably not surprisingly, if you go up to 9 dB, it's almost a factor of 8. Now it's almost because the math doesn't work out exactly correct. But nonetheless, a great rule of thumb is that 3 dB means you're going to be multiplying by 2 the sound intensity level. So what about this whole negative dB? What does it mean to go minus dB? Well, if you have some experience with doing logarithms, if you take the logarithm of a number that's, let's say it's bigger on the top and smaller on the bottom, we'll get a positive number. But if we flip these and have I1 over I2, you'll get a minus number. And so I'll just sort of demonstrate that to you here. You know what? I'm going to actually open up my calculator here, and so we'll do something like this. The logarithm of 3 is log base 10 of 3. Log base 10 of 2. That's log base 10 of 2, or I'll just say, I think the way Google works, you can just do, yeah, that's right. Log of 2, it's assumed that it's already base 10. So log base 2 is 0.3, and as I mentioned, it's multiplied by 10, so you get 3 dB. What I want to do here is to say, If I did the logarithm of 1/2 instead, I will get a minus 0.3. So here it is, so it's minus 0.3. So in other words, and that would be, remember that our formula here is 10 times the logarithm. So for example, 10 times the logarithm of 2, that means going up in intensity by a factor of 2, will give me a 3 dB increase. If I take 1 divided by 2, in other words, I2 is 1, say watts per square meter, and I1 is 2, say watts per square meter, then when I take the ratio of these, I'm going to get a number that's less than 1, and therefore the logarithm of a fraction is going to be a minus dB. So actually you can think of this mathematically as this. Oops. Not sure what just happened. Okay. You can think of this mathematically as this. Remember that the logarithm base 10 of y is equal to x is the same thing as answering the question 10 to the x equals to y, right? So in other words, if that y, for example, was 2, then you could say 10 to the 0.3 is going to be 2. But if that y was 1/2, you could say 10 to the minus 0.3 would be equal to 1/2. You can try that out on your calculator and convince yourself that that's true. It really just does take playing around with these things and trying them out. So for example, each of these examples that I bring up in here, see if you can convert back and forth between them. After a little while of practicing this, you're going to find that you're developing some intuition and some tricks for how to interpret these ideas. But just simply looking at what I'm saying, you'll probably have a very hard time to understand it. So please practice. Try convincing yourself that plus 3 dB is a factor of 2 in intensity. And you could try even saying, flip it around the other way. If I gave you an intensity ratio of 5, what's that difference in dB? If I gave you a difference in dB of 6 dB, what's the intensity ratio? So you should be able to go both ways. Okay? So in other words, minus 50 dB means divide by 100,000. Going back to my calculator here, if we do divide by 100,000, that's 1 over 100,000. Oops, there we go. There it is, minus 50 dB, just as we had predicted. So minus 50 dB means divide by 100,000. So for example, if you're at a concert and the sound intensity is 10 to the minus 3 watts per square meter, and the speaker intensity drops by 20 dB, what's your new intensity? See if you can figure that one out. So here I will get a new sheet of paper here and I'll work that one with you. So if I'm at a concert and I'm going to just write down the numbers, then switch to the camera, the intensity let's say, is equal to 10 to the minus 3 watts per square meter. And I2 is what we want to figure out. We don't know. But we know that the sound intensity level difference is equal to minus 20 dB. Okay, good. So there's a couple so it drops by 20 dB. In other words, it goes down by minus 20 dB. It goes down by 20 dB, or it has a difference of minus 20 dB. We need to figure out what this I2 is. So we know that sound intensity level difference is minus 20 dB. And we know that for every minus 10 dB, it means we've divided by 10 for the intensity. Right? So in other words, a minus 10 dB and a minus 10 dB, each time is going to be divided by 100. So our first minus 10 and our second minus 10, these ones we're going to add to minus 20 dB. Whereas these ones we're multiplying, all of the different, either multiplying or dividing, right? So here we're going to actually divide by 10 and then divide by 10 again. And so together we get divide by 100. So here, if we look at this number right here, we can say that I1, if we divide by 100, that's actually going to give us 10 to the minus 3 times 10 to the minus 2. That's dividing by 100 is multiplying by 10 to the minus 2. And we'll get 10 to the minus 5 watts per square meter. So that's kind of one way that you could go about seeing this thing intuitively, is just saying, okay, for every 10 dB down, we're going to divide by 10. The other way that you could do it is you could say that the sound intensity level difference is equal to minus 20 dB, and that's equal to 10 times the log of I2 over I1, and I1 is 10 to the minus 3. So this is an equation that we could solve by, say, dividing both sides by 10. So we have minus 20 over 10 is equal to the logarithm of I2 over, 10 to the minus 3. And we can actually raise both sides, 10 to the this stuff and 10 to the this stuff. And it turns out that if you raise something, a logarithm, if you raise it to the power of 10, meaning 10 to the log, they undo each other. So this is going to just be I2 over 10 to the minus 3 is equal to 10 to the minus, and this is 2 over 1, so 10 to the minus 2. And finally, I can put these together here. As, let me see here if I can, maybe I just go to the next page here. If we have 10 to the minus 2 is equal to I2 over 10 to the minus 3, I can multiply both sides by 10 to the minus 3, 10 to the minus 3, and these will cancel out, and I'll be giving 10 to the minus 5 watts per square meter is equal to I2, same as we had before. So hopefully that's helping you to get more fluent with how to manipulate these numbers. Okay. And so finally, let's talk a little bit about loudness. So loudness is not the same thing as the intensity. So just like how when we had these two words where we talked about the frequency, which is the thing that you physically measure, the physics word, and pitch, which is the sensation that's associated with frequency, we have loudness is actually a combination, it turns out, between the actual intensity that you would measure, in other words, the watts per square meter, and it also takes into account the frequency as well. So there's another thing called the timbre, which we can talk about later, which has to do with the actual waveform and the envelope of the sound wave. But for right now, let's just think about this loudness as a sensation, psychological sensation, and that is a combination between thinking about both the frequency and the intensity. So while it's true that if just the intensity gets higher, then it feels louder, it turns out that you could also keep the intensity the same and change the frequency, and then you'd have a difference in the perceived loudness. So here's the way that we can think about this here. So roughly speaking, you can think of it as a doubling of loudness corresponds to somewhere between a 6 to 10 dB increase in sound intensity level. 10 phones is defined as the loudness of a pure 10 dB, 1000 hertz pure tone. And so you can actually see there's these maps here that are drawn as a function of frequency. You can actually see that there's different sound intensities that there's different sound intensities that we are actually hearing differently at different for different frequencies. So, for example, one way of reading this chart here would be to say that if you had a 200 hertz signal and it had a sound intensity of somewhere around 10 to the minus 10, it wouldn't be audible. But if you just simply kept that sound intensity the same and you moved up to 1000 hertz, it would be audible. You'd be beyond this threshold of audibility. So there's another way that we draw these contours, and it's like this. We draw this threshold of hearing, and the way that we can use this kind of chart is that we can actually look between what is the thing that, say, a microphone would measure in terms of the actual, say, pressure variations and at what frequency, and then we can convert that into what a human would actually hear it as. So these curves actually convert to the way that we would hear things. And so for example, you can see that the way that these things are defined is that 20 phones is the 20 dB, and 40 phones is 40 dB, and 60 phones is 60 dB, and so on. But you notice they don't have this flat relationship to each other. If they did, then we wouldn't need this kind of chart to look things up. So these equal loudness contours are sometimes called as the Fletcher-Munson diagram, and you will notice that you can see that the sound intensity level and frequency both are considered when we consider what the actual loudness is. So this is very much like a topographic map where the altitude is shown as a function of, say, how far north and south you are and how far east and west you are, as well as a weather map that might show you where the pressure is at different places. So this is called as like a two-dimensional contour plot. So for example, here's a map showing some mountains in a town nearby. This happens to be in Boulder, Colorado. And you can see that as you cross these contour lines, you're going to be going uphill. So in the same way, here I've shown this diagram here, tilted on its side. You can see that as you cross these lines, you're going to more loudness. So in other words, each line that you cross is going to be a higher phone of perceived loudness. So let's practice an example to make this more concrete. So if you hear two pure tones, one is 200 hertz and one is 4,000 hertz, and they're both at the same 60 dB sound intensity level, which one will be the loudest? Which one will you hear as the loudest? So what we can do is take a look at these on the chart here and notice that for the 200 hertz one at 60, it looks like it's at 60 sound intensity level, it's also 60 phones. Whereas for the 4,000 hertz, so this is 4,000 hertz up to 60 dB, this is actually a lot closer to the 70 dB phone level. So the 4 kilohertz tone is heard at close to 70 phones, while the 200 hertz tone is heard at 60 phones. So in fact, the 4 kilohertz tone appears louder. And this probably corresponds to your experience. If you played around with the function generators, you might have noticed that just changing the frequency, you notice those high-pitched sounds, that they sound like they're louder, when in fact they're actually not higher intensity, but because of the way that our ear is hearing, we're more sensitive to those higher frequencies. So that's an interesting thing, and it looks like if you were to go a little bit further, up here up to 10,000 hertz, it looks like we drop off in our sensitivity to these sounds. So the way we can solve this is we say that we look at a sound intensity level and you look for what contour line essentially is being crossed, and that's how you can read it off. And if it falls somewhere in between, so let's say we wanted to find at 5,000 hertz, a 60 dB sound intensity level, what loudness is it? It looks like it falls somewhere in between the 60 and the 70. So I might say this is probably maybe 65 phones or something like that at 5,000 hertz. So so the way that we then can draw that is we look at, this is our 4,000 here is close to 70, our 200 here is almost right on at 60 phones. And so the phones has to do with your loudness. So the last topic that I want to mention is that we lose our ability to hear high frequencies with age. And so this is our hearing loss as in dB. And so you can see that as if you're 25 years old, then you don't have very much hearing loss at these higher frequencies. But as you get older, and the women are a dashed line here, women will lose, let's say, about 12 dB. So by the way, let's kind of quantify that. So that means that let's say that if it was 10 dB loss, that means that the sound would have to be 10 times louder in order for it to be just audible for somebody who's 55 compared with somebody who's maybe a youngster. But if you notice maybe the difference between 55 and 25, you might estimate here, that looks to me to be about maybe 7 or 8 dB difference. So remember, every 3 dB means a factor of 2. So let's say that it was 6 dB difference between 55 and 25. That means that you'd have to, if something was just audible for a 25-year-old woman, and then for a 55-year-old woman, we would have to multiply that intensity by a factor of 4 because of the 6 dB difference. And so remember, every 3 dB means a factor of 2. Now let's take a look at men. So men have significantly more hearing loss as they age. And you can notice here, let's take a look at a 45-year-old man compared with a 25-year-old man. And so you can see here that this is looks like more than 10 dB, right? So let's say it was, oh, I don't know, let's say it was 13 dB, right? So let's say it's 13 dB difference between a 25-year-old man and a 45-year-old man. So if you remember how to calculate this is that 10 dB means a factor of 10, and 3 dB means a factor of 2. So putting those together, you can see that you'd have to multiply the intensity by a factor of 20 for a 45-year-old man just to be able to hear something that is just audible for a 25-year-old man. So hopefully that helps you to begin to see how to read this chart, how to make some sense of things. I think that's all for now, and thank you for watching.